Hello, this is Jack Jackson. In this video, we're going to talk a little bit about relations and functions, and specifically about equivalence relations. So let's go over some basic definitions. We're going to define a relation as a set of ordered pairs. That's any set of ordered pairs. Now, sometimes instead of using set notation like that, we'll use the symbols like this little tilde here, this little squiggle, to say A squiggle B or ARB to indicate that A and B is an element of that relation. And so AB is that ordered pair is an element of that relation, that set of ordered pairs. For example, we say 3 is less than 4, just indicate that the ordered pair 3, 4 is part of the relation less than. And we say line segment AB is congruent to line segment CD to indicate line segment AB, comma, line segment CD is part of the relation congruence of line segment. Or in other words, is congruent to. The first coordinate is called the input. The second coordinate is called the output. The set of all first coordinates, the set of all inputs is called the domain. The set of all outputs is called the range of the relation. A relation in which no two of its inputs, no two of its first coordinates are identical is called a function or mapping. So in other words, in a function, every input is mapped to exactly one output. A function in which no two of its outputs are identical is called an injective function or a one-to-one function. Every input is mapped to exactly one output, making a function, but then in addition, every output is mapped from exactly one input. A relation is a reflexive relation if and only if A, comma A is an element of the relation for every A in the domain of the relation. In other words, it is as a reflexive if A is related to itself for every element in there. It's symmetric relation if and only if when A, comma B is an element of the relation, then B, comma A is also an element of the relation. In other words, if A is related to B, then B has to be related to A. That's symmetric. A relation is a transitive relation if and only if when both A, comma B and B, comma C are elements of relation, then A, comma C is also an element of relation. In other words, if A is related to B and B is related to C, then then A is related to C. So they're kind of linked together in a little chain. And a relation is equivalence relation if and only if it is a reflexive, symmetric, and transitive relation. Two elements A and B in the domain of an equivalence relation are said to be in the same equivalence class if and only if A, comma B is part of the equivalence relation. In other words, if A is related to B, and we denote the equivalence class containing any element of an element A by bracket A bracket. Congruence of line segments is an example of equivalence relation, which we'll prove in this video. Line segments are not relations, so line segments are not transitive, reflexive, or symmetric, or equivalence relations. For example, we never say the line segment is reflexive, but you can say the relation congruence of line segments is a reflexive relation. Another concept that's important is very much related. It's called a partition of a set. So a partition of a set is a set of sets, say A1, A2, up to AN, such that each A sub k of the partition is a subset of S, and the intersection of any two distinct elements of P is empty, so they're what we call pairwise disjoint. And the union of all the sets in P is the entire set S. So notice that a partition of a set S is a set of subsets of S. One element of a partition is a specific subset of S. So it turns out that the concept of an equivalence relation is extremely important in mathematics. It shows up in lots of different areas of math. The following proposition is a particularly important result that shows up in many contexts. It says that a partition and equivalence relation are basically the same thing. Note the two parts of proposition 11 are actually converses of each other. If we have an equivalence relation, that each equivalence class is an element of a partition of the set, and conversely, if there is a partition, of a set, then that partition induces an equivalence relation on the set. Ultimately, every element of the equivalence class is related to every element of the same equivalence class, including itself, but is not related to any element from a different equivalence class. You'll probably see this important result in at least one or two other classes, maybe a course in discrete mathematics, foundations of mathematics, very likely in abstract algebra, or maybe real analysis. It might show up in one or more of those classes. So here's our proposition relating equivalence classes and partitions. If F is an equivalence relation on a set, then the set of equivalence classes forms a partition of S. If P is a partition on S, then the set of ordered pairs formed by taking all possible ordered pairs within each element of S is an equivalence relation. So let's look at the proof. We'll do the A first. Let F be an equivalence relation on set. Now we have to show, so that's the given hypothesis. Now from there we have to show that we're going to get that these equivalence classes form a partition. So by definition, F is a set of ordered pairs, because it's a relation, from S cross S. In other words, the ordered pairs, both coordinates come from S, which is reflexive, symmetric, and transitive. Okay, so let's see what that means. For every element S in the set big S, S comma S is an element of F. In other words, S is related to S, since F is a reflexive relation. Thus, S is going to be an element of that equivalence class S. And so if you union all those, there's at least every equivalence class has at least some element in it, and all the elements are in some equivalence class. So if you union all of them together, you get all of S. So that's the first requirement for it to be a partition. Now the second requirement for it to be a partition is if you take two elements in the partition, two of these subsets, they have to be pairwise disjoint. Or another way to say that is if they have any overlap at all, they have to actually be completely the same thing. So that's how we're going to prove this. Let X be an element of the equivalence class S intersection with the equivalence class T. So X is in both of these two equivalence classes. We want to show that these things have to be the same equivalence class. So by definition of equivalence class, X is related to S and X is related to T since it's in these two classes. Those are ordered pairs that are in this equivalence relation F. Or another way to say it is X is related to S and X is related to T. Because it's a transitive relation, okay, hang on a second. Okay, so because F is a symmetric relation, we can reverse these ordered pairs and they're still in there. Sx and Tx are in F. In other words, we've got X related to S, S has to be related to X, and X is related to T, so T has to be related to X. Okay, so now what do we want to do? We want to show that S and T are the same. These equivalence classes are the same. So we need to take an element in S and show that it has to be in T. Okay, so let Y be an element of this equivalence class of S. By definition, YS is in our function. In other words, Y is related to S. We already have S is related to X, and we have, now what do we have? Y is related to S, and S is related to X. So Y has to be related to X. So Yx is in this relation, F, since F is a transitive relation. Similarly, Y is related to X, and X is related to T, which we already have, right? Says Y comma T is in F. since F is a transitive relation. So by definition, Y is in the equivalence class of T. So everything in S, the equivalence class of S is also in the equivalence class of T. So we have a subset relationship there. Okay. Now, similarly, just got the same argument just going with the other one. So let Z be an element of T. So we just come back to the same argument. That means ZT is an element of S. Z is related to T. But we already have Tx is in F. T is related to X, right? So Z is related to X. Why? Well, if Z is related to T and T is related to X, Z is related to X. Since, why? Because F is a transitive relation. Okay, so now what do we have? Similarly, Z is related to X. And those are both in F, I need to say. Implies Z is related to T. And again, that's because of transitivity, right? Of F. Z is related to X is related to T, Z has to be related to T. And that's what we mean by this being a subset there. That's because F is transitive again. So now what do we have? We have Z is in T. Okay. Well, that means no matter, but Z was an arbitrary element of T, the equivalence class of T. So the equivalence class of T is a subset of the equivalence class of S. Well, now we have the subset going both directions. So that means S and T, those two equivalence classes are the same. So we see that if two equivalence classes are not the same, then they have to be disjoint. Therefore, the union of all equivalence classes is the entire set S, and the equivalence classes are pairwise disjoint. So that's the definition of a partition. So by definition, the equivalence classes form a partition of the set. Okay, that's part that we proved part A. Now let's prove part B. Let's start with the partition, which is this this set of subsets. Get this here. So define a relation F on S so that X is related to Y. In other words, XY is an element of F. If and only if both X and Y are in that same element of the partition for some, one of those elements for some K. Okay. Now let's take any X in S in our set. Since the union of all the partitions is S, there's some K where X is going to be in one of these guys, in one of the P's of K. And X is in the same element partition as self, so X is related to itself, and thus F is a reflexive relation. Now, if X and Y are in F, X is in the same element partition as Y, so Y is in the same element of the partition as X. So say if X is in P sub K, then so Y is in P sub K, then Y is in P sub K and X is in P sub K. It's symmetric, right? So if XY is in F, YX is in F. So F is a symmetric relation. Now, let X and Y be in F, and YZ be in F. X is related to Y, Y is related to Z. They're elements of partition such that xy is an element of pk and yz are in the same one as well. But one of the definitions of partition, the elements of the partition are disjoint. And notice they both have y in them. So pk and pj are the same. And thus x and z, thus x comma z is an f. So we started with x is related to y and y is related to z, gave us x is related to z. Therefore, f is a transitive relation. F is a reflexive, symmetric, and transitive relation. Therefore, by definition, f is an equivalence relation. And then that completes our proof. So when it's all said and done, what do we end up with? Well, we see that partitions can be thought of as equivalence classes, right? And that makes an equivalence relation. That's the part B. And part A says that if you have an equivalence relation, you can think of each of the equivalence classes as making a partition. So really, these are just sort of two ways of thinking of the same kind of concept. So next we will see that congruence of line segments is an equivalence relation. And more generally, we will ultimately see that congruence of geometric figures is an equivalence relation. And we're going to use this symbol here. It looks like an equals, a little squiggle on top. That'll be used to denote congruence. That's our congruence symbol. In particular, equality will always imply congruence, but congruence does not necessarily imply equality. In other words, if two figures are equal, they will be congruent, but if they're congruent, they don't necessarily have to be equal. For two geometric figures to be equal, they must be equal as sets. In other words, they have to be exactly the same figure, same size, set, size, location, orientation, everything. Congruent figures will be the same size and shape, but not necessarily the same place or orientation. Okay, so ultimately we will define two geometric figures to be congruent if and only if there's an isometry. That would be an identity mapping, the translation, reflection, rotation, or glide reflection that maps one of the figures to the other. This works well for Euclidean geometry, and we will study this in our toward the end of the course. However, for the time being, exactly what is meant by congruence will initially be defined for each type of figure, more of an ad hoc approach. So that essential properties of the figure are preserved under congruence. So we take this approach because it makes a unified approach to geometry a bit easier. And it'll also make the transformations a little bit easier if we're only focusing on Euclidean geometry when we get to it. Notice how we use definitions of a line segment and equivalence relation to write out the proof of part A of the following proposition. Notice the correct use of language. Line segments are not reflexive, symmetric, and transitive. Instead, is the relation congruence of line segments that is reflexive, symmetric, and transitive, and is thus an equivalence relation. The outline of the proof is to show that the relation has each of these three properties. In each case, we use the definition of congruent line segments to get the statement about lengths, positive real numbers, and then we use the fact that equality of real numbers is an equivalence relation. In fact, equality of real numbers is really our kind of canonical example of what an equivalence relation is. So what we're going to do here is we're going to now prove that congruence of line segments is an equivalence relation. So here's the proof. Part A. Take any line segment AB has the same length as itself. AB equals AB, and the equality of real numbers is a reflexive relation. Thus, by definition, AB is congruent to AB. Line segment AB is congruent to line segment AB because lengths AB are equal to length AB. And that's the definition of a line segment. Being congruent. Since every line segment is congruent to itself, congruence of line segments is a reflexive relation. Okay, so we got reflexive. Let's go to symmetric. Suppose line segment AB is congruent to line segment CD. By definition, these two line segments have the same length, so AB equals CD. Equality of real numbers is a symmetric relation, so if AB equals CD, then CD equals AB. And by definition, that means that line segment CD is congruent to line segment AB. Therefore, congruence of line segments is a symmetric relation. Now let's get transitivity. Suppose line segment AB is congruent to line segment CD, and line segment CD is congruent to line segment EF. Again, by definition of congruent line segments, that means that the length AB is equal to the length CD, and CD is also equal to EF. Those are lengths now. Lengths are distances. Since equality of real numbers is a transitive relation, that means that AB, since AB is equal to CD and CD is equal to EF, AB has to equal to EF. So, by definition, AB line segment is congruent to line segment EF. So, therefore, congruence of line segments is a transitive relation. So, therefore, by definition, the congruence of line segments is an equivalence relation since it is reflexive, symmetric, and transitive. So, ultimately, what happens is each equivalence class of line segments is the set of all line segments that are congruent to each other, which is all the line segments that are the same length, regardless of where they are located or which direction they point or whatever. Okay, so that's a little bit of an introduction to equivalence relations and congruence.